Next up is Brenda Ogle, who is also a professor in the Department of Biomedical Engineering here at the university.
Thank you. Hello, everyone. I'm happy to be here and share with you a little bit of my experience, which is somewhat repeated or a repetition of what you've already heard. I think what you'll see and what you're reading on this slide is actually my path is just as circuitous as what you've heard before. I went to high school in this area, so not far probably from where many of you are going to school. I was interested in physics at the time. I had very crooked teeth, so I was amazed at what could be done with orthodontia, and so that's what I thought I wanted to do, or go into medical school. So I went to a little college in northern Minnesota, the College of St. Benedict, and I knew I liked math and I liked science, so I continued on with those two majors. In the course of it, I kind of went through this career crisis where I knew what I liked to do, but I didn't know what I was going to do with it. And that's why I think your generation has a huge advantage over my generation, because you have access to the internet. You can see and experience so much before you even commit to it. And I think that is one thing I will try to promote here, is to really explore and to find out things through that important medium. And so because I didn't know what I would do with it when I graduated, I knew I didn't want to teach math necessarily. I thought about medical school, and so I went and volunteered for a year in Mississippi at a health clinic. And I apparently am a strong candidate for the white coat syndrome. I don't know if you know what that is, but basically every new disease you learn about, you either contract or think you have. So I left that experience thinking medical school was not the thing for me. And so I actually nannied for a year because I was so confused about what to do. And as it happened, the father of the family that I nannied for was an orthopedic surgeon. And he said, you know what, you just weren't exposed to the right kind of medicine. You need to come into the surgical suite with me. You'll see everything. You'll be inspired. And I went in and I was not inspired. I was mortified in some ways, but he didn't give up. He said, you know what, also I'm starting a company with a biomedical engineer and we're designing new spinal implants. And I went, wow. I met with this guy and I thought, this is what I'm gonna do. So I finally was exposed to biomedical engineering. And so that's what really I've been doing ever since. I went to school here. I went to graduate school at the University of Minnesota, and then I spent time as a postdoc. You heard what that was at the Mayo Clinic. And if you ever want to be inspired or happy or proud to be a Minnesotan, all you need to do is watch the Ken Burns documentary on the Mayo Clinic, and you will be, in addition to all the wonderful things that are going on here in Minneapolis as well. So I spent time there, and then I was fortunate enough to continue on as a professor of biomedical engineering. And my group works on therapies for cardiovascular disease, and I'll share with you some of that. In my spare time, I try to exercise, but I really like doing somewhat extreme things for me, and one thing I like doing is hiking, and I was fortunate when I turned 40 to conquer some 14ers, they're called, which are 14,000-foot peaks. And I went with some friends of mine, and that's us at the top of one of them, Mount Democrat. So you heard a lot already about some of the causes of cardiovascular disease, and that's really what we're trying to solve. And I don't know if you know it, but the university is a hot spot for pioneering breakthroughs in cardiovascular medicine. The first implantation of a pacemaker, one of the first successful open heart surgeries was conducted right here. And our lab is trying to continue that tradition, not with medical devices, but with trying to develop living therapies. And we're trying to do that, so that's where cardiac tissue engineering comes into play. And really, it's the concept that you can merge tissues and cells living outside of the body and then use them to repair the heart. And as you heard earlier, the cardiac muscle, once it's damaged, as in the case of a heart attack, you don't actually recover new muscle. What happens instead is a different cell type comes in and basically makes a scar. And that's why you continue to have problems after a heart attack, because you're not actually getting that beating function. You're getting a scar that doesn't actively beat. So the cool thing is that recently we've been able to take stem cells outside of the body. And stem cells are a really unique cell type in that they can give rise to all the other functional cells in your body, and they can give rise to cardiac muscle, the muscle that's lost with a heart attack. And if you just put them into a dish and let them, what we call, differentiate, some of them will start to beat spontaneously. Hopefully you can see some of those. That's the promise of stem cells for cardiac tissue engineering, is that we can actually derive beating cells in a dish. The problem is that it's really hard to control their organization and their maturation to functional beating cells. So if you look at the cross-section of a regular heart tissue like this one, you see that these red long things, those are the cardiac muscle cells. You can see that they're nice and elongated, they're oriented, they're working together. And that's part of what we're trying to convince them to do. And one of the ways that we think you can convince them to do that is by arranging the proteins outside of the cell, and that family of proteins is called extracellular matrix proteins. They're just outside of the cell proteins. So we take those and we're using them to develop bioinks, and we're depositing them with different 3D printing techniques. And I know you all are experts in 3D printing because it's all the rage, but you can print proteins and you can print cells. And one of the ways that we do this is with a multi-photon-based printing technique. And basically what you do is you put your extracellular matrix proteins in this little reservoir, and when you expose it to light, those proteins get cross-linked in this cool little meshwork. And the resolution with this technique is about 1 micron. So you can actually make a structure like this that sort of mimics the packing that we want in the organization for cardiac muscle. And so we just finished a study, and this is sort of the blown-up view of that. These are the struts that we printed in purple, and the red things are the cells, and these blue round things are the nuclei of the cells. And I'm just going to show you a short clip. We had fun because KSTP came out to our lab and did a piece on this. And I think it shows you not just about the research, but just how things operate in a research lab. And so even though I hate to see myself on a video, I'm going to show this really
So to say
quick
a new
clip.
breakthrough could change the way doctors treat people with heart disease. 5 Eyewitness News reporter Matt Belanger was in the lab today and got a first-hand look at this new technology. Pretty neat, Matt.
Yeah, not only is it remarkable, it could have a big impact on the medical community. Engineers used 3D printing technology to create a patch out of cells that beats just like a human heart, and they hope it could one day offer an option for doctors to reverse the currently irreversible damage caused by a heart attack. This tiny patch could bring huge change to how doctors treat heart disease. This patch is actually beating, like a heart.
Exactly. And that was the aha moment.
Biomedical engineering professor Brenda Ogle worked with her graduate researcher Molly Kupfer at the University of Minnesota to develop the patch. Look closely at this magnified video and you can see the cells of the patch beating just like a human heart.
They started to beat. They knew what to do. And at that point, we thought, well, this really could be a therapy for the heart.
That orange circular gasket is where the structure is fabricated.
The patches are created using 3D printing technology. This machine uses lasers to make the necessary microscopic connections.
Wherever the laser hits, basically it links them together.
The engineering breakthrough could have a big impact on the treatment of America's #1 killer. After a heart attack, the human heart is damaged, which often leads to future health problems. When researchers tested the patches on mice after simulated heart attacks, they created a reversal of that damage after 4 weeks. It's the moment they've been waiting for 15. Sure is. Now, the next step for these engineers is to try that patch on the heart of a larger animal, and they just got the money from the National Institute.
Okay, so that gives you a sense for one thing you can do in the lab is to basically from the bottom up create a tissue that might be used to repair the heart. We're also using different 3D printing techniques to make larger heart-like or chambered structures in the lab. And it's really 3D printing that allows that for the first time, that you can have open space within a structure. And so I'll just show you, here's sort of a digital template that we use for the muscle. We're going to soon be adding, we hope, vessels. And we use an extrusion-based modality for this application. So what you'll see here is, what I hope you can envision or realize is that within this structure are open cavities that are similar to the ventricles and atria of your heart. And so here is the structure beating. It's very small. It's not the size of a human heart, but it's about 1.5 centimeters on its longest axis. And then you can see the wave of electrical activity that propagates through that structure. And so this is the first time this has been accomplished using 3D printing in this way. So we hope that it's used for model systems and maybe eventually for a transplant. So thanks, everybody.
Questions? Questions about the heart?
Go ahead. Yes, you. Mhm. From what? No. Okay, your question is about Henrietta Lacks and the No, these are actually called human-induced pluripotent stem cells. Do you know that terminology? Maybe you've already been exposed to that. But basically, you can take any cell from your body, a skin cell, a blood cell, and using genetic transcription factors, genetically modify the cells so you can revert them to a stem cell state. That way you don't need to use, it can come from an individual who's consented to be using those cells. It doesn't come from an embryo, but it still has all of the potential of those cells. Yeah. Yeah, no. Yeah, no, but it's an interesting story, and it really informed a community about how to start utilizing cells from individuals and what's the best way to go about that, and to also inform people of what's happening if they consent to donating cells and tissues for research. That's a good question. Sure.
So once you revert those cells to the stem cell state, how do you make them into like a heart type cell so that they beat? How do you get them to just change into that type of cell, or is it just kind of random?
Right. So the question is, how do you convince them to become the cell type you want? And I would say that's a huge field of research right now, and that's exactly what we're doing too. We know that there are certain, they're called growth factors, that can bind to a cell and basically tell them this is the direction you're supposed to go. And we're finding that these extracellular matrix proteins, collagen is one of those, actually are potent signalers that specify which way it should go. So if you give them the right combination of factors, they'll just go to cardiomyocytes and not to anything else. And that's really the breakthrough that lets some of these therapies happen. Maybe last one, or are we okay
We
on
can do
time?
2 more.
Oh, two
yeah.
more, great.
Yeah.
How do you control the rhythm of the patch or the cells that are going on in the heart, or does nature just take care of itself?
Right. So these will spontaneously beat because they're sort of early, they're almost embryonic in their functional state. But you can also pace them with electrical pacing, either with field or local stimulation. You basically artificially depolymerize the cell, or depolarize the cell, and then that's what starts the signal. And then those cells are all coupled by gap junctions, so the ions just start flowing, and that's what causes them to beat synchronously.
Okay, and last question.
Okay, so earlier you said that the cell can be taken from anybody and worked on and transformed into what it is.
Right.
So is it possible that once it's transformed, just because it's from somebody else, it could react differently with the next person or something?
Could you repeat the question?
Right, I'll repeat it. So the question is, if you can take a cell from anyone, basically, and make stem cells out of them, what if you use those cells and put them into another person? Would they react?
Right, but is it possible to react differently?
Right, so you would have the same thing that you would with an organ transplant that would go from one individual to another. And you can use immunosuppression to sort of get around that response. But the kind of cool thing is that maybe if you have a disease or disorder, we actually might have enough time to take the cell from you, expand it, make it the cell type you need, and then put it back in your body.
Great, thank you, Brenda.
Yep.